Hello children, in the previous classes of refraction of light, we discussed about how refraction can take place through a glass slab, and as well as we discussed even about the refraction of light through a prism also. And especially in the previous class, dear children, we discussed about the simple applications of refraction. There we discussed what is the apparent depth, what is the real depth, how apparent depth and the real depth are related to the refractive index. In today's class, dear children, we will be discussing the only very important topic is that total internal reflection. Means if you want to understand that, we need to understand even about critical angle also. So, in today's complete session, we will be discussing about critical angle, total internal reflection, especially we will be discussing about total reflecting prisms. I mean, how total internal reflection can take place in the case of prisms we will discuss. And finally, we will see the difference between normal reflection and total internal reflection. Children, before getting to the topic, once again let us recall what happens when light travels from one transparent medium to another transparent medium. So it's very clear that other than normal incidents, in a general case, what happens? Light bends. It depends whether it is moving from rarer to denser medium or denser to rarer medium. What happens if light moves from optically rarer medium to optically denser medium? So it slows down, due to which what happens, dear children? It moves towards the normal. But what happens if light moves from optically denser medium to rarer medium? It moves away from the normal. So this is a point which we are going to take in today's class. So it's very important. What happens if object is placed in a denser medium? So children, if object is placed in a denser medium, obviously light rays will come out of that object in all directions three-dimensionally. All directions three-dimensionally. So light rays, if they are moving from denser to next transparent medium, rarer, what happens? They will move away from the normal. Why? Because the speed of the light is going to get increased in a rarer medium when compared with a denser medium. Now let us take that case where object O is situated in a denser medium such a way that light rays are moving towards a rarer medium. So it's very important. So we have taken a case where object is placed in a denser medium such a way that light rays are moving from denser medium to rarer medium. So it is very clear to us what is that? Light rays will move away from the normal. Now let us try to understand this situation, dear children. Let us say here is first light ray, it is the second one, here is third one, fourth one, fifth one, sixth one. Let us try to notice what will happen to these 6 light rays. So in the first light ray, as it is normal incidence, so whenever light incidence normal to the interface between the two mediums, it will go undeviated. So this is no refraction, children. First light ray, so here refraction cannot occur. This is a case of no refraction it is. But what will happen to second light ray? It is not normal incidence. Rather, all these light rays are oblique incidence. So they are incidenting obliquely. So whenever here light is moving from denser to rarer medium, it moves away from the normal. So here you can notice. So this is a second light ray. So it is going away from the normal. Children, this will be the angle of incidence and this is a corresponding angle of refraction. And what will happen to second light ray? Sorry, it is the second light ray. Now let us consider the third light ray. Of course, as usual, this third light ray is moving from denser to rarer medium. It moves away from the normal. And this is the angle of incidence and it is the corresponding angle of refraction. Corresponding angle of refraction R2. Whereas this is angle of incidence for fourth light ray. So even fourth light ray also is moving from optically denser medium to rarer medium. So what happens? It moves away from the normal. And this is the fourth light ray. It is a fourth light ray and this is a corresponding angle of refraction. Corresponding angle of refraction. So try to notice here, this second light ray, third light ray, fourth light ray, they are moving from denser to rarer medium, of course, due to which what will happen? The speeds up, means their speed increases. So what will happen? They will move away from the normal. And here only we have to notice one important thing. What is that here, children? Here this light ray, if you can see, in a denser medium, as angle of incidence is increasing, then what is happening? In a rarer medium, the angle of refraction also increasing, which is a very, very important point. Very means very much important point. Just try to notice here, in a denser medium, as the angle of incidence is increasing and the corresponding angle of refraction is also increasing here. Which means what? Due to which what is happening? This refracted light ray is approaching the interface. Which means what here? As the angle of incidence in a denser medium is increasing, this refracted ray, look at here, first it is going like this, next it is like this, next it is like this, next it is like this. Means what is happening? This refracted light ray, as like a, what we can say, the clock, okay na? So that will be the second one. So it's like a clock, it's chick, 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 chick. So this is how actually refracted ray is coming towards the normal, and for a particular angle of incidence, means like this, you keep on increasing the angle of incidence in a denser medium, the refracted light ray will be approaching. But for a particular value of angle of incidence, let us say, particular value of angle of incidence, what happens, that refracted ray goes along the interface. So this is how actually light ray grazes the surface. So it's very much important. Very much important. So this is actually the special angle of incidence. This is a special angle of incidence for which the angle of refraction is going to be 90 degrees. 90 degrees. That particular angle of incidence in a denser medium for which angle of refraction in a rarer medium is 90 degrees is called critical angle. This is called critical angle. Very important. Simple children. Very simple. What is happening? In a denser medium, if the angle of incidence is increasing, the refracted ray is approaching the interface. At a particular value of angle of incidence, what will happen? The refracted ray grazes the interface. It is going along the boundary between the two mediums. Which means what here? The angle of refraction is becoming a 90 degrees. So this particular angle of incidence only we can call it as a critical angle. Then you may get a one doubt. Sir, what happens if light ray incidence with a more than the critical angle? For suppose here, if angle of incidence is greater than the critical angle, what happens if light ray is incidenting such a way that the angle of incidence is greater than critical angle? Then children, no more refraction. Then what happens? This light ray gets reflected into the same medium. Means in this case, at this surface, dear children, this surface acts like a reflecting surface, like a mirror. This surface acts like a mirror. So this is what actually a concept of total internal reflection. So very important, children. So here we have to understand very important thing is that here what actually critical angle. When angle of incidence exceeds critical angle only, what happens? Total internal reflection takes place. Children, let us write the definition of actually what is a critical angle. Then it will be very easy. After that, we can understand what actually total internal reflection. I mean, we will see the conditions when total internal reflection can occur. It's very important. Fine. Okay. Fine. Let me rub this. So here, let me take this case simple manner. So children, here is a boundary x, y boundary, and here is, let us take, here is a two light rays actually. So this is normal incidence, it went like this, and this is for which actually critical angle. So here what happens? Light ray is grazing the surface, so that here angle of refraction became 90 degrees. Children, this is a simple case of actually a critical angle case. It is critical angle case. So here is a optically denser medium, and here is optically rarer medium. So what is the critical angle, dear children? Look at here. It is nothing but the angle of incidence only, the critical angle. So children, this is how actually we can define the critical angle. The angle of incidence in a denser medium, dear children, for which the angle of refraction in a rarer medium is 90 degrees, then that particular angle of incidence only we can call it as a critical angle. Now what happens, dear children, when angle of incidence exceeds critical angle? For suppose this is what actually now. So this light is like incidenting like this, look at here. So here is angle of incidence greater than the critical angle. Then what will happen, as we discuss, so light will get totally internally reflected. Then what are the conditions when this light ray is undergoing total internal reflection, children? So here light ray must obey the two conditions, then only what happens, it will undergo total internal reflection. Let us see that here. So total internal reflection conditions. So here conditions at the rate total internal reflection. So what are these? What are those here? The first condition is that, dear children, light must travel from denser to rarer. Children, very important. Light always must travel from denser to rarer medium, whereas angle of incidence must be greater than critical angle. So children, if any light ray can obey these two conditions, then that particular light ray will undergo total internal reflection. Undergo means what? Light ray has to travel from denser to rarer medium. At the same time, angle of incidence must be greater than that of the critical angle. So children, this is what actually critical angle, and there are the conditions for total internal reflection. Now we will see, dear children, on which factors does critical angle depend and how critical angle is related to the refractive index. It's very important. And after that we will see the applications of total internal reflection. So now we will see on which factors does the critical angle depends. Now before going to discuss on which factors does the critical angle depends, so first let us try to derive the relationship between critical angle and refractive index. Then we can understand the factors on which critical angle depends in an easy manner. So for that, dear children, let us take only a special 90 degrees. So children, this is a special case where particularly we are showing the critical angle case. Children, here is a denser medium. Let us say its refractive index is mu. Let us say it's a mu2, or mu1, and it is a rarer medium whose refractive index is mu2. Now dear children, at this surface xy, let us apply the Snell's law. Children, once again let us recall the Snell's law. What is the Snell's law? It is a refractive index of second medium with respect to first medium is equal to the sine of angle of incidence by sine of angle of refraction. So very important. Means the refractive index of second medium with respect to the first medium. So that is, we should write like this: refractive index of second medium by first medium is equal to sine I by sine R. So this is actually Snell's law of refraction. But dear children, look at here. In this case here, I is equal to C. As I is equal to C here, R is equal to 90 degrees. Fine. And let us say here a rarer medium is air. So then obviously mu2 is equal to 1. Then let us take a mu1 as a mu only. Now substitute here. So mu2 is equal to 1. Fine. By. So refractive index of this medium, that is a denser medium, is a mu only. Mu is equal to sine I. So in the place of I, we have to substitute the critical angle, that is sine C, by sine R. R is equal to 90 degrees. So it is a sine 90. So it is going to be 1 by mu is equal to, it is sine C by. Children, sin 90 is equal to how much? 1. So it is a 1. So from here we get 1 by mu is equal to sin c. 1 by mu is equal to sin c. Or we can write like this. Mu is equal to 1 by sin c. Children, it is a very important relation. Very important. So from this, it's a very clear. It's very clear. What is that here? Critical angle and refractive index are inversely proportional to each other. Which means what? If refractive index is more, obviously critical angle for a given pair of mediums is going to be decrease. If it is more, it will be less. If it is less, it is more. So children, this is how actually refractive index and critical angle are related. It's very important. Now let us see the factors on which critical angle depends. Factors on which critical angle depends. So children, hope you copied. Mu is equal to 1 by sin c. Or you can write here c is equal to sin inverse of 1 by mu. So anything is okay. Or this can be written as a cosecant c also. Cosecant c, that is 1 by sin theta is equal to cosec theta. So mu is equal to cosec c also we can write. Okay, fine. So this is how actually critical angle and refractive index are related. Now, how critical angle on which factors it depends? Children, the first point is that very important. It depends on wavelength. It depends on wavelength or color, let us say wavelength or color of light. Wavelength or color of light. Color of light. Children, so we know that it is critical angle is inversely proportional to the refractive index. Am I right? Just we derived actually. Mu is equal to 1 by sin c. It can be written as c is equal to, if c is a very small, then sin c can be written as a c only. That is accepted. Okay. So c is inversely proportional to mu, which means what? More the critical angle, less the more the refractive index, less the critical angle, or less the refractive index, more the critical angle. But actually, let us recall once again how refractive index and wavelength are related. Both are inversely proportional to each other. I mean what here? This we can write like this. Lambda. It is a lambda. Now try to relate these two. So our intention is to relate this. Means for a given pair of two mediums, dear children, more the wavelength, more the critical angle. Less the wavelength, less the critical angle. So here critical angle is directly proportional to the wavelength. Children, for a given pair of mediums, for a given pair of two mediums, critical angle is more for a color for which the wavelength is more. That's what, children, the critical angle for red color is greater than that of the critical angle for violet color. Why? Because for a red color wavelength is more, so more the critical angle. For a violet color wavelength is less, so critical angle is less. This is the first point. Now the second point is the temperature. It is a temperature. Children, again let us recall c is inversely proportional to the mu. Fine. Now you forget about the critical angle. Let us try to think about the relation between refractive index and refractive index and temperature. Children, we have discussed the topic where we discussed about the refractive index, the factors on which refractive index depends. The very important thing is that refractive index depends on the temperature. But how? Refractive index is inversely proportional to temperature. Inversely proportional to temperature. Which means what? 1 by mu is proportional to the temperature. Means what here? More the temperature, less the refractive index. Less the temperature, more the refractive index. Now, our intention is to make a relationship between these two. So, critical angle is proportional to the temperature. It's very important. Critical angle is proportional to the temperature. So, which means what here? So, as the temperature increases, what will happen? Critical angle for a given pair of two mediums. Critical angle for given pair of two mediums also increases. So, children, once again I am saying you here, try to understand. First, you should understand how critical angle is related to the refractive index. Then it will become very easy to us to understand how critical angle is related to the wavelength. At the same time, how is it related to the temperature. Children, critical angle is inversely proportional to the refractive index. And refractive index is inversely proportional to the wavelength and temperature. That's what critical angle is proportional to the wavelength. At the same time, it is proportional to the even temperature also. So this is what actually critical angle, and on which factors does it depend. Now dear children, here we will see three very important cases when refraction can take place, when critical angle, when is the critical angle condition, and when total internal reflection takes place. Just we have to remember examination point of view. Look at it children, case 1. So what happens if angle of incidence is less than critical angle? Then what will happen? Normal refraction can take place. Normal refraction can take place. If angle of, see, light ray is moving from denser to rarer medium, but angle of incidence is less than the critical angle, then normal refraction takes place. Whereas case 2, what happens if angle of incidence is equal to critical angle? Children, still refraction only takes place. Very important. Still refraction only takes place. Still refraction only takes place. But the specialty of this is that in examination they may ask this question: what is the maximum angle of incidence to occur refraction? Children, till critical angle, refraction can occur. Refraction can occur. It's very important. Means the maximum value of angle of incidence till where refraction can occur is the critical angle. Then what happens? The third case. So case 3 is that if angle of incidence is greater than the critical angle, then dear children, total internal reflection can occur. Then total internal reflection can occur. It's very important. Children, we have to remember the two conditions. Light ray must travel from denser to rarer medium. At the same time, angle of incidence must be greater than the critical angle. Then only what happens? Total internal reflection can occur. So children, so these are the three things which we have to remember. Very important. Now we will see the applications of total internal reflection. Especially how total internal reflection can occur in a prisms. That is what actually we are going to discuss now. Now we will see total internal reflection in total reflecting prisms. Total reflecting prisms. Total reflecting prisms. Children, these are the prisms in which one angle is 90 degrees such a way that other two angles are 45 degrees each. 45 degrees each. Now we will see how total internal reflection can occur and what way we are going to use the total reflecting prisms. Children, first of all, the total reflecting prisms are used to deviate light ray through 90 degrees. Children, it's very important. So here total reflecting prisms are used to deviate the light ray through 90 degrees. So in order to deviate the light ray, children, 90 degrees actually. So what is going to happen inside the actually prisms? Of course, it is completely based on total reflecting prisms. In fact, total reflecting prisms can work on the principle or phenomena called total internal reflection. Now let us see, children. So let us see how total reflecting prism to be arranged in order to deviate the light ray through 90 degrees. So look at here. So this is a position. So here is the prism. It should be arranged. So here is A, here is B, here is C. Such as that, children. So light ray is incidenting normal. It's a normal to the BA. Children, we know that whenever light incidents normal to the interface between two medium, either it is from rarer to denser or denser to rarer, what will happen? It will go undeviated. So this light ray will go undeviated. But dear children, at this point, try to understand, this is a point very important where we have to concentrate. Let us say it's the point P. So at point P, dear children, at P, what is happening here? Light is trying to move from glass to air. That is what? Denser to rarer. And don't forget that, dear children, this is 90 degrees and here is 45 degrees and this is also 45 degrees only because it is total reflecting prisms. Now we need to find the angle of incidence at BC surface. At BC surface we need to find out actually. Now teacher, look at here. Children, this is 90 and it is 45. Obviously it is also 45 degrees only. Then what is this, dear children? So this is going to be 45 degrees. So this is angle of incidence at BC surface is 45 degrees. So children, here we need to know first of all what is the critical angle for glass air interface. Children, critical angle for glass air interface is 42 degrees. Glass air interface is 40 degrees, whereas for water air interface is 48 degrees. But children, in this case what is happening here? Look at here, at a point P, light is moving from denser to rarer medium. And what is the angle of incidence? 45 degrees. But what is the critical angle for glass air interface? 42. Which means what here? Angle of incidence is greater than the critical angle. So here, the two conditions required for total internal reflection are obeyed by this light ray. So then what happens? This light ray at this point P will undergo total internal reflection. So it will get reflected. Children, by default as it is getting reflected, it will become normal to AC. Normal to AC. So this will go like this. So try to understand. If there was no prism, actually this light ray would have traveled like this. But what angle is getting deviated? 90 degrees. So your light ray is getting deviated through 90 degrees. So this is a case actually where we use in a periscope actually. It's a very, very important. So this case of the prism, total reflecting prism is used in a periscope. Fine. Now teacher, let us see the case 2. So here case 2, there is application of 2. So in this case, it is used to deviate, light ray, through 180 degrees, Teacher, actually in general, the plane mirror only will deviate the light ray through 180 degrees. How? Look at here. So here is plane mirror. Okay. If any light ray incidence normal to its surface, then what will happen? Its path is retraced. So it will again bounce back in the same medium. So with what angle the light ray is getting deviated? It is 180 degrees. Similarly, dear children, to deviate the light ray through 180 degrees means other than plane mirror, we use prism, total reflecting prism to deviate the light ray through 180 degrees. For that, how the total reflecting prism to be arranged? Look at here. So children, so this is how actually total reflecting prism to be arranged. This is case 2. Fine. So it is a, so that it is a 90 degrees. It is a B and here is 45 degrees and here also 45 degrees only. Now dear children, so it's A, B, C. So here BC is nothing but what? It's a hypotenuse. Now in this case, light ray to be, it's incidenting normal to this BC. Children, as we discussed earlier, so whenever light ray incidence normal to the interface between the two mediums, it will go undeviated. So what will happen? This light ray will go undeviated like this. So this is how it will go under here. But let us say this is point P. Once again, let us say it's a point P where light ray is trying to go from glass to air. That is what? Denser to rarer. So let us see here at a point P. At a point P, what is happening? Light ray is moving from denser to rarer medium. But what is the angle of incidence at this AB surface? That we have to find out. Children, this is 90, it is 45 and this will be 45. Now obviously, this is going to be, children, 45 degrees only. 45 degrees only. This is the angle of incidence. So at a point B, light is moving from denser to rarer and at the same time, the angle of incidence is greater than the critical angle. So here angle of incidence is greater than the critical angle. Then what will happen? Light ray will undergo total internal reflection. By default, it will become, the refracted light ray will become parallel to the base, parallel to this BC, So this is how actually it will go. It is going like this. But children, again at this point, let us say this point is a Q. So at this point, what is happening? Light is trying to go from glass to air, that is denser to rarer. But what is the angle of incidence here? So it is a 90 degrees. This is 45 degrees, and here also 45 degrees. And it is a 90 degrees. 45 degrees is gone. Then how much is left, children? So this is angle of incidence is equal to 45 degrees. Again, it is greater than that of the critical angle. So here at a point P, at a point Q, what is happening here? These two conditions are fulfilled. So at a point P, at a point Q, what is happening here? Light ray is undergoing total internal reflection. So here what will happen here? This light ray gets totally internally reflected. By default, it will become perpendicular, that is a normal to this BC. So it will go again undeviated only. Now actually look at here. Actually here light ray has to go like this, but it is 90 degrees deviation, 90 degrees deviation. But whereas here also light ray has to go like this, but again here light ray is getting deviated to 90 degrees. So 90 plus 90 is how much here? It is a 180 degrees. So children, this is how actually based on total internal reflection, total reflecting prism deviates the light ray through 180 degrees. So this is a case where we use in a binocular actually. So this is a case we use in a binocular. So very important. Children, in the first case, light ray is deviated through 90 degrees. It is used in a periscope. Whereas in the second case, the light ray is getting deviated through 180 degrees, and this is used in a binocular. Now we will discuss the third case, where actually there is no deviation. So it's very important. Here deviation is 90 degrees, here deviation is 180 degrees. Third case where we are going to discuss, there is no deviation. Then what is the purpose? What is the purpose? To erect the inverted image. It's very important. That's what in a case 3, the prism is called erected prism. Erecting prism. So very important. Means in the third case, light ray is not going to get deviated. Rather, it will get shifted as like a glass slab, dear children. Just let us recall a glass slab. Glass slab does not produce any deviation. Rather, it can shift. So similarly, so here is case 3. So what is happening? To erect inverted image. To erect inverted image, total reflecting prism is used. Look at here how it is going to be. Children, this is total internal reflective prism. Let us make a little bit big prism so that it will be more fine. It is a A, that is 90 degrees. It is a B, 45 degrees, and here is C, again it is a 45 degrees only. Children, here is an object, let us say. Let us put here is one object AB, or else PQ. So PQ. From here, light rays are coming like this. Just wait. Here is this light ray, or else let us take a small object so that it will be more convenient to us to draw the diagram. So this is PQ is the object, and here is from here light rays are coming like this. Children, look at here at this point, light rays are moving from rarer to denser. Then obviously what will happen? Refraction can take place. As they are moving from rarer to denser, they will move towards the normal. So this is how actually light ray bends. Light ray bends. Try to understand, children. You should be very careful. You should be very careful. And here this light ray also get here. But the children, at these 2 points, they are trying to go from denser to rarer medium, and by default what happens, the angle of incidence will become greater than the critical angle, which means what? At these 2 points, light rays are going to get totally internally reflected. So here this light ray will go like this, will get like, sorry, it is bending. No, it should not bend, it will go straight. It will go straight, and this light rays will go straight. Now at this point what will happen? Denser to rarer, normal refraction will take place. So this light ray, So we'll get like this, and this light ray also will go like this. Now look at here addition, try to understand, very important thing is that, very important. So look at this here, the light ray which is coming from Q, it's Q, it's Q, it's Q. So this is going to be Q dash. Whereas the light ray which is coming from free, P, just try to just trace out this light ray, trace out this light ray. It is a P dash, P dash. Actually PQ should be like this, but what is happening? It is getting inverted. It is. So here, this is how actually we can see here. But dear children, do you think that here light rays are getting deviated? No. This light ray actually it has to go like this, just shifted here. And this light ray has to go like this, just shifted. That's what in this case there is no deviation. There is no deviation. So these are the three cases where total internal reflection can occur in total reflecting prisms, and they are used in a various situations. So these are the best examples where we can show total internal reflection in a prisms. Now dear children, we will see how total internal reflection can occur in a equilateral prisms, then we will see in a right angle prism also. So there are the two important cases which we have. So now we will see how total internal reflection can occur in equilateral triangle, in a equilateral prism. Let us see an equilateral prism, very important. Equilateral prism. How total internal reflection can occur in a equilateral prisms here. Okay, fine. Now case 1 teacher, look at here. So this is, let us say, equilateral prism. Here is equilateral prism. So that here is 60 degrees, and each angle is 60 degrees, each angle, even angle of the prism also 60 degrees. Let us name it as A, B, C. Teacher, let light ray is incidenting normal to this AB, normal to this AB. Then what will happen? This light ray, children, so as it is incidenting normally, so let us say it is incidenting normal like this. Then what will happen? This light ray will undergo like this. It will go like that. Undeviated it will go. Children, this light ray will go undeviated. But dear children, at this point, let us make a normal here. Let us make a normal. Children, this is 90. So it is a 90, it is a 60. And this will be 30 degrees. This will be 30 degrees. Then obviously dear children, this is how much? This is going to be 60 degrees. This is going to be 60 degrees. Means angle of incidence at AC surface is how much? 60 degrees. Now let us recall the critical angle for glass air interface is how much? Just 42 degrees only. So at this point, light ray is moving from glass to air, that is denser to rarer. Similarly, at the same time, the angle of incidence is greater than the critical angle. Then what will happen? Light ray will undergo total internal reflection. With what angle? Children, what will be this angle of reflection? This also will be 60 degrees only. And by default, children, this light ray will become again normal to BC. So this will go undeviated. Of course, it is somewhat bending here and there, but it should not bend like that. So it has to go straight. It has to go straight. Children, this is how actually total internal reflection can occur. Total internal reflection can occur in the case of actually equilateral prism. Now we will see how total internal reflection can occur in a right angle prisms. So that is going to be the last case in applications of the prisms total internal reflection. Now look at here, children. So let us take a right angle triangle, right angle prisms. So this is, so here is A, B, C. So this is 90 degrees, this will be 30 degrees, and this is going to be 60 degrees. Children, let us consider that light ray is incidenting like this, normal to AC, normal to AC. Now obviously children, it will go undeviated. it will go undimmed. So it is a very simple case from here to here. So this light ray will undergo, of course it will go undeviated, but this is a point where we have to notice, where we have to concentrate here. So this is a point where light is going from denser to rarer medium, denser to rarer medium. But what is the angle of incidence? Children, this is 90 degrees, 90, 60, and this is going to be 30 degrees. But dear children, this will be 60 degrees. So angle of incidence is a 60 degrees. Means at this point, light is moving from denser to rarer medium. At the same time here, angle of incidence is greater than that of the critical angle. Then what will happen? Light will undergo total internal reflection. So children, this light will get totally internal reflect like this. Will get very important. Now at this point, children, now again we may get one doubt. Here light is moving from, at this point is going from denser to rarer, but glass to air, denser to rarer. But what will be the angle of incidence? Very, very, very important. Children, it is not that if light ray will move from denser to rarer medium, total internal reflection can occur. It is not that. Even angle of incidence also must be greater than the critical angle. Then only total internal reflection can occur. It's very important that we have to we have to concentrate that 2 points actually. Fine. Now dear children, now what will be this angle of incidence? Look at here. Very, very important. Children, so it is 60 means this is 60, no doubt about it, and this is 30. So clear. So 30, it is 30, 60 means this to be 120 degrees. That is fine. And here it is 90 degrees, right? 90 degrees. Then what will be this angle of incidence? This will be how much, dear children? This will be here, angle of incidence is 30 degrees. 30 degrees. What is the critical angle for glass air interface? 42 degrees. Children, at this point here, light is moving from denser to rarer. It's very clear. But angle of incidence is not greater than critical angle. It is less than that of the critical angle. Then what will happen? Normal refraction can take place. So normal refraction means it is moving from glass to air, denser to rarer. So it will move away from the normal. It will move away from the normal. So children, this is how total internal reflection can occur even in right angle prisms. Very, very important. So we have seen how total internal reflection can occur in total reflecting prisms, equilateral prisms, and here right angle prisms. Children, now once again let us see, let us check once again, let us think what is the difference between normal reflection and total internal reflection. Very, very important. Children, the very, very important thing is that if you can take a normal mirror at any angle of incidence, children, reflection can occur. It's very, very simple. Means any angle of incidence, normal reflection will take place. But what about total internal reflection? It is not that. Light ray must travel from denser to rarer medium, and one more condition, critical angle must be greater than that of the, angle of incidence must be greater than the critical angle. That is the first difference. And one more thing, dear children, during a normal reflection, some amount of light gets absorbed. It's very, very important. Means for every reflection, at every point of reflection, some amount of light gets reflected. But whereas during this total internal reflection, dear children, 100% of the light will get reflected. Means the amount of the 0% of the light will get absorbed. So what will happen? The final image, whatever we are going to get with a total internal reflection, will be the brightest one. We'll have with full clarity we will have when we compare with a normal reflection. So that is how total internal reflections are very, very, very special. We are not only that, dear children, here. So based on this total internal reflection only, mirrors can occur, and even optical fiber cables. Optical fiber cables are completely. So what is the principle which is in an optical fiber cable? Total internal reflection. Even let us take the diamond. Why diamond is so special? Just because of light is, once light will enter into the diamond, dear children, so that light will get trapped inside. So that what will happen? Light will undergo many times reflection, so that that diamond appears as if it is sparkling actually. So these all are a glittering of diamond, mirage, and optical fibers, looming even. These all are digital applications of total internal reflection. So in one special class definitely we are going to discuss only applications of total internal reflection. I mean how mirage can occur, how looming can occur, how optical fiber cable is working, and even how why actually diamond is so special. That will make a special video on the only applications of total internal reflection. So children, this is actually today class. So in today class, just let us recall what is that topic very important which we discussed. Children, only one thing, total internal reflection and critical angle. That's it. So we have to remember two important conditions. What are those here? Light ray must travel from denser to rarer medium, and whereas angle of incidence must be greater than critical angle. And you need to practice digital how total internal reflection can occur in a prism. Okay, na? So this is actually today's class. In the next class, we'll be discussing a new more topic. Okay, children. Thank you very much. All the very best.